really narrow down. And part of the utility of transmitting every second or every 2 seconds is that you get, for most animal tracks, it really oversamples the track and allows you to get accurate location.
5 meters, roughly how far is the average distance from the base station to?
About 5 kilometers. Something. Okay, we published a paper on this. I was very happy. One last thing I'll say about the localization is that we are now trying to get rid of the constraint of putting GPS DOs. We may skip it in one base station in order to get. It's not even important to have, as long as you compensate for the clock rate ratios, then you get accurate localizations. We'll probably put 1 or 2 base stations with GPS DOs in order for the absolute to be able to compensate to a correct absolute clock rate, but it's not really important. We collaborated with a group in Aachen. This shows 2 different corrections of a trial run we did in the Hula Valley. Both of them are corrected. The uncorrected are all over the place. We used clocks that were really inaccurate in this sense. And what was kind of cool is that we used this system that we deployed to track wildlife, but really as a field test bed with multiple receivers, known performance. We switched the code that the base stations run so that they can switch between different oscillators of the USRP, and we moved to inaccurate oscillators and let the system run this way and try to compensate. That's what the graph shows. Okay, the tags went through long evolution, partially because I never built anything like this really at small scale. So we started from evaluation boards. We used them basically to make sure that the transmitters can actually transmit the signals that we need at a high rate, and that we would be able to localize them to within nanoseconds or tens of nanoseconds in the lab. Then we miniaturized the design. We tried 2 designs. One is CC430s, single chip with a radio and a microcontroller, and 2 chip designs. The two chip designs were smaller. These were hand assembled. Then we manufactured commercially exactly the same design to make sure that we can manufacture them at large quantities. And then we started miniaturizing them using smaller components, even smaller components. And that's the next generation, which uses different chips. So let me say a few words about the chips. So the first generation were MSP430s with very little RAM. It was kind of a mistake, but not really a mistake. I chose the specific chip for the physical size, not for anything else. I chose the smallest chip. When I said mistake, these are 4 millimeter by 4 millimeter chips. I really chose them for the PIDs. I chose QFN chips that I could still solder myself. There are BGA chips that are the same size and would have larger memories, but I wanted to avoid the BGAs. And CC430s, and on the 256 bytes of RAM, we used bare metal. We didn't use anything there. You really can't use anything. And this was really the constraints. The ecologists wanted more features, and it was really impossible to do that. So when TI came out with a new generation of chips, the CC1310, 1350s, that combine in the same 4 millimeter form factor an ARM processor, a radio, and another ARM processor that controls the radio. We switched to them. We use TI RTOS, the vendor's operating system for these chips. And we've implemented a range of new features. Not all of them are completely implemented. Some of them are. For example, they have long-range modes. They have spreading and error correction modes that we use to send IDs, and we measure this to work over distances of about up to 8 kilometers. You can download data from the chips. I think I have the chips if somebody. I have the tags if somebody wants to see them. They have connectors that we use to add sensors and memory boards, and so on. The challenges were batteries. It's not that difficult to power these using a large lithium battery, but once you go to very small lithium batteries or to silver oxide batteries, they become very difficult to operate. I'll say a few words about this. Reliability, both the hardware and the firmware, really very difficult issue. And sometimes the ecologists report failures. Some of these failures were really due to firmware bugs, but some of them were due to the sloppy way that they were soldering them, and it's hard to know what's what. Antennas, they're physically small, so it's very hard to get the signal out of a very small tag. prototyping and production. I'll say just one thing. We use I think a Bay Area company called Circuit Hub. There, for me, they're not in the Bay Area. They're out in the internet. You fill in the form. You upload your design. You choose parts, which parts you want them to solder onto the board. You choose the quantity. Let me. I'll switch. It's just incredible. Let's move on here. You choose the quantity, so this is one of our designs. As you can see, the number changing. And if I click order here, and one of you wants to supply their whatever. No. I mean, initial. Okay, that's. I mean, you can order small quantities, but they're still expensive. Initially, they made a mistake in pricing, or it was introductory pricing. They would produce, 2 for $20 each. We ordered a few of these until they realized that it cost them $800, no matter how simple the design. So now we order batches of 100 even for testing. So you click order, you pay with the credit card number, and you get the bag via FedEx a few weeks later. Just unbelievable. You don't need. I mean, you learn about manufacturing as time goes by because they run into problems and they send you email. But really, it's really incredible. There are some interesting issues with power management on the smallest tags. The battery doesn't really power the transmitter. There is a capacitor. We use 330 microfarad capacitors, and the 330 was chosen to support 8 millisecond transmissions. That's what we transmit, and a little bit before and after, so 10 millisecond bursts. When they're charged, they're 3 volts because the batteries are 3 volts, and you need them not to go below 1.8, in which the processor will stop, will crash, will reset, whatever. We use them very extensively. One problem is that they're leaky. Because they're leaky, they limit the total lifespan of a tag, and also you can't really prepare tags ahead of time because the capacitor will leak before the tag is deployed in the field. And we fixed that using Frank, the engineer from the Netherlands, who designed really a clever 3-part circuit to disconnect the capacitor, which is easy. That's not a problem. So if when the tag goes into deep sleep mode, it can tell the MOSFET to disconnect the tag. That's no problem. The problem is reconnecting, because if you just reconnect this, like you throw a switch, the capacitor will drop the voltage of the battery immediately. So the high impedance battery will see a very low impedance capacitor, and you'll get a reset in the best case, and a hung system that will drain the battery in the worst case. So what he did is he basically extended the Miller plateau of the turning on of the MOSFET. That's what you see here is the Miller plateau, and it's over a second or two or something like this. So it charges the capacitor slowly, and then you can start working. And this really enables the use of the smallest silver oxide battery. So they use 337, 317. They're really tiny. I added this, so I've shown this presentation before, but this is for you guys. There are some interesting reflections on firmware. One is that this combination, even without the MOSFET, the combination of the when you power tags from reservoir capacitors, it places a very complicated difficult to satisfy constraint on scheduling. So it's what you want to minimize. What you need to minimize is not just the total energy drained out of the battery, but you need to do this slowly. So if you've transmitted an 8 millisecond transmission, you need to let the power recover, the reservoir capacitor recover over 5 seconds before you can do anything. And that's scary. So you build this over on top of an operating system. Does the operating system has some wake-ups that you don't know about, some housekeeping that will crash the system? So it's scary. It was easier to do this bare metal to make sure that it's okay. The firmware is easy. You look at the firmware, and even if it's complicated, it's not easy. It's not difficult to prove that it will only wake up once every 5 seconds or one every 8 seconds. But the operating system, you don't know. And even if you measure this for some version of the operating system when it gets upgraded, is it still true? It's really scary. The other thing is that as the chips got more complicated, these ARM chips got more complicated, it's really becoming difficult to avoid the vendor operating system and the vendor drivers. The vendor drivers are really impossible to avoid. That's not a big issue. When these chips wake up, they don't go to your code. They go to the TI boot code. The boot code looks at the flash to find out whether you want which regulator you want to use to configure. The OS and the drivers are in ROM, which means that if you use a different operating system or whatever, then you lose that ROM and flash is becoming a constraint. And also, the most amazing thing is that the hardware is really not fully specified. So there are some things about the hardware that they used to specify for the standalone transceivers, like how long does it take to wake up the synthesizer, because we transmit on a very precise schedule, and we need to wake up the synthesizer. Do we need a millisecond before, half a millisecond before? Now they don't tell you. They tell you, tell us when to wake up the radio. When do you want to transmit? In 37 milliseconds, we'll wake up the radio on time, the synthesizer on time. They don't tell you how long it takes, and it's embedded in the driver. There are many registers in the technical manual that says, TI internal, use our drivers. So it's becoming difficult. Oh.
You got about one more minute.
OK. 1 minute? OK, base stations, I won't say much about this. They do have some custom electronics in terms of filters and amplifiers. Like I said, they're on tall towers when we can get them. I'll switch over this. You've seen this. There's visualization, Android visualization. There's software to run the receivers without the system so that you can find tags, you can test tags, and so on. This is kind of interesting. This is the receivers also assess the amount of energy on every RF channel that we use. And what you can see here is the interference. And you can see that there are quiet times. It's relative, so different base stations are in different places, but it's really relative. It's completely irrelevant. But you see here, there was more noise, quiet during the night, and then very noisy during the day, military transmitters turning on or whatever. And this was really key to do this visualization, because before we had the visualization and before we had the code to measure this in the system, the ecology would say, why does the system not localize my tags? I mean, I don't know. And sometimes it was because it's just there is too much interference and the system becomes deaf. So you deploy something in the system in the field, you need to know what's going on. I'll use the last few seconds to say what are we doing now. So more deployments. These deployments in the Netherlands, in the UK, it's a huge amount of work to support them. It's not a turnkey system that you send. They need to install software. Some of them run the base stations on Windows, on Linux, and so on. The transmissions right now, we use FSK transmissions. They're really a limiting factor. We use them because that's what the integrated transceivers can do. And we're going to move, at least on some tags, to more effective modulation, to BFSK modulation, maybe some other variants. We also have a prototype with a standalone miniature transmitter, but we can transmit BFSK. BFSK is very to gain those 15 dB in sensitivity, you need to be coherent with the frequency of the transmitter, which makes the finding the transmissions more difficult. So we need to do a two-dimensional search over time and over frequency, as opposed to what we do now, which is the FSK. We use detected FSK, which is very frequency insensitive. So that's going to be an issue. More features for the new generation tags, and also this the multiple techniques to get rid of the GPS clocks and accurate clocks in general. For example, one thing we're going to do is the beacons will transmit. They transmit every second, but they'll transmit a random sequence of plus ones, minus ones, either two codes or codes inverted, in order to coarsely synchronize the different receivers if their computer clock is off. OK, that's it.
Great.
Sorry for going over.
So I think we're 2 minutes over, so if you need to dash, now is a good time. If not, we have room for another 13 minutes or so. And so I'd like to open things up to questions. Any questions?
So I noticed that you didn't take into account the Z dimension any.
In
like the original equations that you had up there, you don't take into account the Z dimensions. Did you enforce that all of the towers are at the same altitude?
No, the equation, you could put Z into the equations. You'd need one more base station. That's one more unknown to estimate. So, and the code, we can run the code in 2D or 3D. In 3D, the receivers are not spread out enough in height in order to get. So what happens is that you do get Z estimates, but the variance of the Z estimates is 200 meters as opposed to 5 meters or 10 meters for the standard deviation of the XY. So it's really kind of useless. I mean, if you average over an hour, you'll find that you'll find the height. But if you look at one, it could be 200 underground, which is useless. We'll put altimeters on the tags. Again, that brings back the issue of how do you get the data out of the altimeters. And also, initially, I mean, I'm not an expert in sensors, so I farmed out the choice of the altimeters to the ecologist. And it's not easy. I mean, the Bosch altimeters that they found are probably not that good for absolute heights, but they're probably very good for relative heights. So.
Could you not include another receiver on your towers, so double up, so have one higher and one up?
You need one 5 kilometers up. You don't need one another 50 meters up. So actually the receivers are spread out even in height fairly nicely. So actually, here. So the round ones are receivers, and you can. So that's a valley. The valley is at 70 meters above sea level, and there are hills on both sides. So 8, for example, is at close to 900 meters. So it's 800 meters above the valley, and it's still not enough to get good Z localizations. You need one either on a very high balloon or ideally in space. So that's GPS. I mean, they're all around you. That's what makes it possible. Yes?
Well, what's the average lifetime of the battery? What's the biggest, obviously transmission is a big consumer battery. How much does the microprocessor
there are two consumers. One is the transmissions. Once the microprocessor turns on when it transmits. So during transmissions, there'll be maybe 20, 30 milliamps going out to transmit. And if you don't transmit, it'll be maybe 1 or 2 milliamps. So it's really negligible. So transmissions is one consumer. Leakage in the capacitor is another one. And it leaks these capacitors. I mean, we may switch from tantalum to ceramic, and we may go. So these leak. We didn't measure this, but the datasheet says that they leak about 25 microamps. So that's about 1,000th of what they during active mode, which means that if you transmit 8 milliseconds and then you wait 8 seconds for the next transmission, you use roughly half the power on leakage. And that's why we never transmit less often. The ecologists would like to transmit every minute an ID transmission or whatever. We just don't know how to do this with very small batteries right now. There is, I mentioned before, there is a group building similar systems, ultrasound for tags in PNNL in Oregon. And they've developed, they faced exactly the same problem, and they developed their own batteries that are more suitable for powering transmitters than silver oxide. They licensed or gave the design to a Chinese company making batteries, but they're not really making those batteries.
So it seems like if you have that transistor that has low enough resistance.
Very bad idea, but it doesn't work. Because the capacitor, in order not to go down below 1.8 volts, needs to have energy for 5 transmissions or something like this. And if you fill it up, you transmit once and you let it drain, you spend 80% on leakage. Also, the other issue is that in order to protect the batteries, we do charge the capacitor through a resistor, through a 1K or a 3K ohm resistor, so that the batteries never see a very low impedance. It affects them badly. And we we simulated the effect of that that resistor, that current limit. We also tried more complicated current limiting. That resistor wastes a small amount, 15% of the power. Because of that nice Miller plateau, the capacitor charge, when we open up the MOSFET, it charges up the capacitor at constant current. And when it charges at constant current, exactly half of the energy goes into the capacitor and half of the energy is wasted on the MOSFET. So, I mean, if somebody has better ideas, we'll be delighted. And we even looked at, we did look at energy harvesting chips from TI, from Linear. And they're really highly, first they're large. They're, again, not large in their book. I mean, they're 4 millimeters, another 4 or 3 millimeters on the side. But they're really highly customized to specific applications. And they're not, for example, they're customized to energy harvesting. So for example, if you can use them to get energy out of a high impedance source, like a solar panel or a tiny battery. But because they're built for energy harvesting, they'll get energy out of that high impedance source as much as they can. They'll never stop. So they, again, will leak out the entire thing.
On the interference, what frequency are you transmitting on?
We are the license free 434 megahertz mostly.
You're not in a public band. You're in a you're at a license.
No. We are in a public band.
On how long you can transmit and how you
we are within those bounds. We are within those bounds for Europe. I think the US is actually more lax, but we are within the bounds for Europe. I should say, we are within the bounds for Europe. We did compliance testing once, but it's really impractical to do compliance testing because it needs to be with the correct battery and the correct enclosure and so on. So you end up spending $50,000 for each variant. It's really not feasible. Oh, not here. Oh.